We are going to discuss about microinstruction optimization. Primarily the idea is to reduce the instruction word length so that we can save on the ROM size. So let's first consider what the problem is. What are the inputs and output specification for this problem? What do we start with and what will we end up with? The inputs that we require for is a horizontal microinstruction format. We start with the fact that we assign separate bits in our microinstruction to all the control signals. So that results in a horizontal microinstruction format. And the other input is a symbolic microprogram. Remember, we discussed in the last class that we can either optimize your microinstruction word length based on the architecture, or we can optimize it for the application. So in this case we are talking of optimizing for the application. Of course, optimizing for the architecture is a problem subset in the sense that typically it will be much easier to find the set of disjoint control signals by analyzing the architecture. So we are not considering that problem. Of course, you can apply the same techniques as we are developing here for that particular situation as well. Typically this will be a more complex problem because the number of microinstructions or the number of states in the machine are going to be fairly large. So these are the two inputs, and starting from these two inputs, the output that we need to generate is a microinstruction format, which essentially says how many fields, what is the width of the fields, and which control signals are assigned to which field. So this is what is the microinstruction format specifies, and that is the output of our. I will illustrate this with the same example that we had used for earlier cases. So the same GCD example, just to recollect what we had. I have shown it over here, but basically we have one state where we are waiting for the start signal, inputting, then checking whether it is unequal, then we are checking whether it is greater, followed by doing some subtractions of the smaller value from the larger value, and then finally setting the output register as well as the end of complete, and then going back to the start. So now the one input that we have for performing this GCD example is the symbolic microprogram. Let's look at what the symbolic microprogram is. And this is a symbolic microprogram. Let me go over this. So we have, corresponding to the 7 states, the outputs that we generate, we have 7 microinstructions over here. In each microinstruction in the symbolic microprogram, what I am specifying is which are the control signals which need to be activated. So if you look at the first one corresponds to, just to give you an equivalent, so corresponds to that state. This is what we are doing in state S1 or S0, whatever. And that particular thing, so for performing this start bar, what do we need? We need 3 things. We need to select the status. So status select has to be set so that I select the start as the status input. We need to have a sequencer microinstruction. The sequencer microinstruction has to be, sequencer instruction. Sequencer instruction has to be that it is a conditional jump. So I need to set the sequencer instruction. Then the third thing that I need is the branch address. So these are the 3 control signals that need to be activated to be able to perform this state. Similarly, when you go to the next state, S2, where we are actually selecting the input to the registers R1 and R2, which are the 2 registers which are going to store the X and Y values, if you recollect the data path we had. And then we are going to select the multiplexer input, load the register values, and again we have to have a sequencer instruction which will be a continue at the next instruction. There will be no branch address required, there will be no status select required. But we are also going to clear the end of computation. So now this is what I am writing over here in terms of my symbolic microprogram. So status select, sequencer instruction, branch address. These 3 control signals are active in this particular microinstruction. R1 select, so this goes to the multiplexer. This is the multiplexer input for register R1, R1 load, R2 select, R2 load. Clear end of computation, that particular flip-flop, clear it, and sequencer instruction. So you can see that branch address as well as status select are missing here. If I go to the next state, in this state I am checking whether it is not equal. For checking the not equal, I have to select the status to be the not equal status input. So this is a select for the multiplexer. The sequencer instruction will be again conditional jump and branch address. Again, next time we are checking whether it is greater or not. So again status select will select the greater sequencer instruction branch address. Now I am performing one subtraction. So I am selecting the input of the subtractor, the first input operand of the subtractor, second input operand of the subtractor, and then because I am also going to load the output of the subtractor into the register, so I am selecting the R1 multiplexer, R1 load, sequencer instruction. So here what I am going to do is I am going to do an unconditional jump. So sequencer instruction will be unconditional jump and the branch address. Status select is not there, but similarly I am going to here do everything else is same except that R2S and R2 load, sequence instruction and branch address. Finally, if once I jump out from here, if you consider the control flow, so I am going to come out here and here I am saying end of complete. This particular thing has to be preset. Now the computation is complete. R3 has to be loaded. It will get the value from the register R1. Sequencer instruction is unconditional jump and branch address, and I will go back to this. So this shows, so what we are seeing here is, please remember one thing, I am only writing which are the control signals which need to be activated. I am not considering their value. As of this moment, I only consider those control signals which are active and not what value they need to take to perform the actions. So this type of a thing is a symbolic microprogram. Of course, as I said, one could also have been writing these in terms of micro operations. Please remember, you can be doing it in terms of control signals or micro operations. This is in terms of the control signals. Micro operations to control signals, you have to have a mapping. So here I am writing it directly in terms of control signals. So if I take that input output specification slide, so this is the symbolic microprogram that I had referred to. So one input is covered. What is the other input? Other input is a horizontal microinstruction format. A horizontal microinstruction format is nothing but the set of control signals that I have. So I have these control signals. I just named them A, B, C, D, E, F, G, H, I, J, K, L. I am also putting in brackets whenever the width is more than 1. Some of the control signals have a width of 1, it's 1 bit, but some of them have, like say, this is 2 bits, this 2 bits, this branch address is 3 bits, and so on. So 9, 11, 5, 16. So my micro instruction word length is 16. So if I don't do anything else, if I want to maintain the maximum concurrency as well as I don't want to make any, so I can develop a microprogram which will be nothing but directly translating that symbolic microprogram into a binary bit pattern, and which will be used to program a control ROM. And the width of this control ROM will be 16, the length will be 7. So I can get this 16 into 7, so many bits, and that can be used as a control ROM. And sequencer, we have already seen the design of the sequencer, and so I can complete my control. So now what the problem that I am trying to address is, for that particular symbolic microprogram, can I reduce the width less than 16? Okay. Is there any shareability? Is there any, can the control signals share the same field? And that is the issue that we are trying to address. I follow the same approach as what we had done before in some other context, and I draw what's called, either I can call it a disjoint graph, I think a more common name is merger graph. But please remember, we come across merger graph in other situations. This is a. So now what I have over here is, I had drawn a node for each of the control signals that I had. So I had A, B, C, D, all these control signals I had drawn a node. And once I had drawn the node, I am drawing edges between these nodes those nodes which are disjoint. Basically the notion here is two nodes are disjoint if there is no microinstruction when they are invoked simultaneously. If you look at this symbolic microprogram, we can see that how does this happen. So if you look at this, this was A, this was B, this was C. If you look at B, sequencer instruction is appearing in all this should have been small I. Sequencer instruction is appearing in all the micro instructions, all the steps. So what is going to happen is it cannot be disjoint with anything. It needs to be invoked with, so that is the reason B is completely isolated. I cannot have B disjoint. So if I consider, so there is an edge if there is no micro instruction where the pair of control signals are activated simultaneously, then there will be an edge. Even if they are activated simultaneously even once in the set of control steps or in the set of micro instructions, silence please. In the set of control, in the set of micro instructions, even if they are invoked once together, then we will not have an edge here between those two nodes. So in this case A and D, if you look at A and D corresponds to status select and R1 select, and status select and R1 select do not appear here simultaneously. So I will have an edge between A and D. So I have to examine each of these pairs of control signals and then I can draw an edge between them. So I will get a merger graph. It can be called a merger graph because from that I am merging. The information that it is representing is that these two are disjoint or they are mutually exclusive.
So in the slide regarding horizontal format, how do we get the word length of 16?
How do we just add up all of them. So the word length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 13, 16. It's just basically an addition of a horizontal microinstruction format. We are not doing any encoding whatsoever. So all the control signals that are required, they are all present in the format. Okay. So obviously this is an expensive format in terms of the number of bits that are required, and but that's a starting point because from there we can go and reduce. So once I have this merger graph, so what we are going to do is fairly intuitive. So basically we will follow the same approach. We will try to identify cliques. Cliques are, as I said before, are complete subgraphs in which every node is connected to every other node. So if you want to look at some cliques, so this is for example a clique. So we don't get cliques of more than 3 nodes over here. There is another clique is ALF. So there are of course many cliques, but we want to identify a set of cliques, and because we are doing a partitioning, which means that all the nodes should be covered by one clique, and there should not be, the same node should not be present in more than one clique. So I am not generating my control signal from multiple fields because each of these cliques are going to map onto one field. If I say that A, D and L is one clique and I make a field out of it, that means that particular field will contain control signals for A, D as well as L. And that can occur because they are disjoint. So there will be no control step where both A and L are active, there is no control step where both D and L are active, there is no control step where both A and D are active. So I can generate this. So in this case I started by doing this. So let me generate one clique, which is, let us say, ADL. Another one is CH. So and another one is EK. And nothing beyond that is possible. Of course, as I mentioned, this problem is a complex problem. but presently we are only handling simple cases, but there are very advanced algorithmic techniques available for doing this type of a partitioning. We are not going into those details right now. So what we have over here is a certain microinstruction format. So I started from this, which ended up with 16 bits. Once I do this partitioning, I can have A, D and L in one field, CH in another, EK in another, and you can see that among the other control signals they do not join with each other. They are not disjoint. They have to be invoked sometimes, so that's the reason I cannot. Okay, but now if I do this completely, let us say ignoring everything else, so this is one method of doing reduction in the microinstruction size, the bit size, but what we end up is we don't get very good advantage, because now I try to encode this and let us see what happens. I ignored many factors, which we will see that how do we take care of those factors subsequently. So if I look at A, D and L, A was a control signal which was 2 bits wide. This was 2 bits wide, it was status select. D was a control signal which was, so this is status select, it was 1 bit wide, it was R1 select. L was a control signal which was EOC preset. So if I join these three, I can basically do it in 2 bits. So I can reduce them, I can encode them in such a manner that I can actually do it in 2 bits. We will also see that why it is possible to do that in 2 bits in a moment. So now let us look at this CH. C was 3 bits. C happened to be 3 bits, it was a branch address. H happens to be 1 bit, it was 1 bit I am not writing, EOC clear. I can again do it in 3 bits. This is 2 bits. But if I come to E and K, what is E and K? E was R1 load and K was R3 load. When I consider R1 load and R3 load, can I do it in 1 bit? I will require 2 bits. The reason I will require 2 bits is I need to encode not only the fact that R1 is to be loaded, R3 is to be loaded, but also the fact that no operation. So the set size is not 2 but 3 which I have to encode, because there will be micro instructions when neither I need R1 nor I need R3. There are such micro instructions. So that means that I will actually need 2 bits. So the reduction that you get over here is only 3 bits instead of 4 that you could have got. Actually, let's say 1 plus 1 plus 1 plus 1, you should have got 4 bits, but the reduction that you get is only 3 bits, which is 13 bit. So actually when it comes to, so the applying click partitioning, let us say without really bothering about what's going to be the word length, what is going to be the nature of the signals, is not going to give you much benefit. So there are other issues that one need to consider which makes the problem little more complex. So what are the issues when I try to do this click partitioning? What are the issues that I need to consider? Let's talk of, and we will also see that how these issues can be handled in my partitioning. I had to reflect some of the control signal properties, and how do I reflect the control signal properties and also the set properties. Let me talk about what I mean. When I talk of cost reduction, here the cost means there is an optimization problem, and here the cost is the word length. The microinstruction word length, or the number of bits that the microinstruction requires, is what I am trying to minimize, and that's what, when I say cost, that's what it means. It's a non-linear. It's non-linear in the sense that if you take 2 control signals, you will require 1 bit, let us say. But when you take 3 control signals, you will require 2 bits. When you go for 4 control signals, you still require 2 bits. So for example, if you have a merger graph of this nature, so if I try to, so these are, let us say 4 4 control signals. So if I try to extract clique, typically clique partitioning will try to get, so these are the maximal subgraphs which are connected, so I may actually end up taking all these 3 together. So if I take all these 3 together, I will require 2 bits. And then I will require another 1 bit for, so if this is A, B, C, D, so I have one, so let me draw here. So I can get one partition which is of this type, I can get another partition which is of this type, and in this case the cost of this will be 2 and this is 1, and whereas in this case both will be 1. Generally when you try to do a clique partitioning algorithm, this is actually preferable because this is the size is larger than, so we try to extract maximal complete subgraphs. But in this case we can see that because of the fact that the increase, so that when you are trying to merge, so there is a, it's not, the reduction is not sort of linear, it's not that as you have more of them the reduction is. So in this case when you go from 2 to 3, there is no reduction in terms of the cost because the number of bits required goes also increases from 1 to 2.
So don't you have to take care of no op in this case?
Yeah, I am talking of, let us say these control signals do not require a no op. If you have to take no ops, then we have to add one more to it. See, there, as I said before, we will again come to that point in a, there are signals which require no op, there are signals which do not require no op.
Why does that mean no cost to ABC?
ABC I had to encode.
No, but ABC can be 1 bit wide each, and they are exclusive, so why do you need?
Okay, yeah, so yeah, let me, okay, so I should not give that argument, I should, let me talk in terms of, even in terms of, let us say no ops. Okay, so you can, basically the number of bits that you require does not change linearly, that is the issue. So the nature of the signals will determine that. Yeah, the point is correct that if all of them are only 1 bit wide and they are all, let's say, select type of a signal, then we require only 1 bit, then I will not require 2 bits. But you can have the same argument for 2 to 3 or 4 to 5 and so on and so forth. You can consider one of the signals could be no op. So the point that I am trying to make is that as the size grows larger, it is not that when you increase the size, the cost reduction is linear, it's non-linear. Sometimes there is a step jump and sometimes there is no change. So this fact also has to be reflected in, after all, typically when you are merging control signals, you are going to talk of small numbers. So these things are important. Generally such things can be ignored if one is talking of doing such type of optimization where you are going to merge tens or hundreds of signals into. So that's not going to happen. It's only few. We are going to 2, 3, 4, 5, 6. So these are the type of control signals which are going to merge into a field. So it is important to actually reflect what the cost computation is rather than. The other thing is the nature of control signals, whether the default value is fixed or don't care. This is the, so because if the default value is fixed, that means we have to also include no op, and that also has to be counted as another operation. Whereas the default value is don't care, then I don't have to bother about that. So we will consider how to handle this. We can mark the nodes which are, depending on which type of node it is, whether it's a fixed type or a don't care type, and reflect that in clustering. When you are doing the merger, we can take care of this fact. And let us see how it works for the example that we have. So we have the same graph here as we had before. What I tried to do is, if you look at the control signals, there are some control signals in this case which needed a fixed default value. This one needed a fixed default value. This one needed a fixed default value. These are the control signals which needed E, G, H, K and L. So what I have done is I have marked E, G, H, K and L separately. So when I am trying to do, when I try to combine, I will try to take care of them. So the way I can work is, if you are grouping so when I am doing my click partitioning, or when I am doing my clustering, at that time I should, if I merge two control signals which are both of them are, let's say in this case of this type, nodes of this type, then what happens is I need an additional no-op. But if I merge this with a control signal which doesn't have a default value, okay, so I can take care of these, whether what is the nature of this, and then I can make an estimate based on what is required to be, how it will help in reducing my control signals. So doing the same thing, so taking care of this, I can do my partitioning. But before that, let me also point out the third part, which is very important, which is the width of control signals. Previously when we are not reflected what is going to be the nodes, what is the size of the nodes. So if you combine a node which is of 2 bit with another control signal which is only 1 bit wide, you obviously are going to get reduction of only 1 bit. The other bit of the control signal is not really going to be used for merger, because it may happen that because we have drawn the edges and the other control signal may not be disjoint, so it's not going to help you in doing more merger. So if you have control signals which are wider, then you can make multiple copies of the same node with bit number. So what happens is, if you have A and if you have B and there is an edge between them, but A happens to be 2 bits wide. So what you can do is, you can actually bitwise you can do it. You can do A1 and A2 and you can make B. Of course they will be disjoint, sorry, they will not be disjoint, they will be, of course, be concurrently activated, but as far as whatever are the edges that are present here, they will be added. So now finally you can create a merger graph in which each of the node is only 1 bit. So this will help, because let us say you had this situation when you had this C which was connected to here. Now the C was connected to both of them, and so you may be able to combine both of them. Whereas if you are trying to, so A1 will combine with B and A2 will combine with C, instead of previously, because B and C were not, there was no edge between them, you could either have taken A with B or A with C. So I could have only been able to merge these two. So I can have multiple copies of the same node with bit number. So once I do this and apply both these criteria in generating my partitioning, so what I am doing is I am evaluating the cost of the cluster, and I am doing that so I can end up with a partition of this nature. So I replaced A with A1 and A2, so I can merge A1E, A2G, B1 and B2, of course they do not merge because they are sequential instruction bits which are going to be there all the C1 with H, C2, C3 again do not merge, because the branch address, the C has only one edge with H, so, and H is only 1 bit, so you can only merge with one, C2, C3, IL, JK. No, so I had to calculate. So there are, so you actually have to know what the default values are, and you have to take care of the default values. Basically, each time you create a, let's say in this case, each time you create any type of a click, let's say this is a click, you evaluate the value of this click, okay. So all the clicks, and then you have to select a set of clicks which will minimize it. Evaluate the cost of it. This is 2 bits, this is 1 bit, this is 1 bit, okay. But when I put them all together, I can find out how many bits this will require. That you have to look at what the signals are.
How about signals which require default values? I mean, how do you decide which click you want to put them in?
So what the, no, so you see, if you require nodes which are default value, and if let's say you combine these two nodes which both of them are default values, okay, so then I have to add So if there is a clique, let's say, which contains both these, so then I have to have a no op as well. So I have to evaluate this value as 2 bits and not as 1 bit. If but both of them do not require, then I will evaluate it as 1 bit.
It's not clear, sir.
So like in the example where we had one of them with 2 bits, one of them with a default value, and say another them with just 1 bit with no default value, then what will be the cost of this?
No, I don't get your point.
Sir, the previous clip which you had drawn in the figure. Yes. A, L and D, what will be the cost of this?
Okay, so okay, so this is, I am not taking this to be 2 bits, so I am actually breaking them down into A1, A2. Okay, so this is basically each one is a bit. Okay, so there is going to be, what I am trying to do, because I am trying to remove the multi-bit signals, and I am going to generate only 1 bit values. So now I am counting the number of bits. Yeah, I think there is one point that I have ignored. So this is, there is a problem over here as okay, I think let me clarify this point in the next class. So I need a few more slides to do this, so I will do that in the next class. Okay, so let's continue with this, or we will discuss it once I finish this point, because I think there is a point that I have missed, and to answer that I need to do that. Okay, we will come back to this. So let me continue with this. So once we have generated this number of bits which correspond to the minimum microinstruction format, which is based on generating, once you have generated these cliques and we have identified them, and then you can, based on the optimized format, you can generate the binary microprogram. Okay, which is just a pattern of zeros and ones. But even once you have the binary microprogram, it's possible, because all the optimization that we did before is based on only the activity of, whether the particular control signal is active or not. The individual values are not considered. It is possible that some of the columns may be compatible. The implication here is that you may have a value, you may have a column which is of this type, okay, another column which is of this type. So these two columns are compatible because they do not require a value which is, so this can still occur. So this particular fact will not be detected in the first stage. The reason it will not be detected in the first stage is, oh sorry, okay, yeah. So this will not be detected in the first stage because we are not still considered the value. So it may be happen that there is a signal which is active here, and there is another control signal which is also active here. So they are not disjoint because both of them are active, but their active values are same. So it may be possible that we can actually merge these columns and still reduce the width of it. And this can be done exactly in the same manner as what we had applied before. So if we make again another compatibility graph with columns and draw which are the columns which are compatible, then I can reduce, again generate a set of cliques on this. So in this case, let us say I can say that C1 and C4 are compatible and they can merge into one column, and C2 and, C1 and C3 and C2 and C4. So C1, C3 can merge and C2, C4 can merge, and we can generate two columns out of this. So this is only based on actually the binary bit pattern, and it does not at all depend upon the control signal. So what we are doing is, once we generate the binary microprogram, we can do this. So based on the optimized format, we generate the binary microprogram. Based on the compatibility between columns, we draw the compatibility graph. Again apply click partitioning to eliminate redundant columns. Basically what you are saying is, if the same set of values can be generated by one column, you can merge two columns and we can generate the same set of values, we can do that. At this stage, this does not require any decoding, because what it essentially means is the output that is coming from the ROM so this is your microinstruction register. So this particular output can be sent to not just to one place, it can be sent to multiple control signals. And this can be used to reduce your width of this. Okay. So to sum up, the microinstruction optimization steps that we have discussed are: we generate the symbolic microprogram that we generated for the GCD case, and we design a horizontal microinstruction format that is just putting together all the bits that are there as control signals. We optimize to generate the fields in the optimized format. This is the step that we were discussing, where we try to get the cost of each of the clicks and do that. We generate binary microprogram. So once we generate the binary microprogram, we can again do the compatibility graph between the columns and eliminate redundant columns. And once we eliminate redundant columns, we design the decoders and fan-out logic. So the decoders are basically to take care of, the fan-out logic is to take care of the second step. When we are reducing the columns, we need a fan-out. The decoders are to take care of when we have joined initially when we have joined control signals into the same field, we need the decoder. So if there are multiple, when we have multiple control signals into the same field, then we need the decoder coming from here, which can generate this. When we have multiple control signals, let us say R1 load and R3 load. Let us say we merge both of them into the same field. Then we have to say that 0 is R1 load and 1 is R3 load. If we do that, then we have to. But as I said, when we are merging these two, we have to have a no-op. So we can say 0, 0, 0, 1 and let us say 1x. We can have this, and based on this 1, we decide whether this. So this decoder will take these two inputs and generate the R1 load and R3 load. So whenever we have a set of control signals.
Sir,
yeah.
Is there any advantage of doing the merger based on columns after doing the reduction based on fields, or can we do it the other way around with the same effect?
No, we cannot do the other way around, because the fields are not as yet decided. We cannot initially we have a horizontal microprogram. So if you actually merge the columns initially, then you are you cannot do then how do you make the fields? Because the control signals are already joined together to form multiple control signals in the same column. They are no longer disjoint from the point of view of the symbolic microprogram. If you want to do it, it's possible, like what you reflect that. Basically, the implication is let us say if two columns, see initially you have a horizontal microprogram, so if you have two columns which are, let us say, disjoint, and you define one column, so what its implication is, wherever this appears, wherever either of them appear, you have to say that it is appearing. So let us say if I take something, R3 load is disjoint, let us say with EOC, okay, so these two are disjoint. So if I take these two columns and initially make it one column, then what I have to, wherever this appears or wherever this appears, all the control signals, which with this appears, there will be no edge, whichever this appears, there will be no edge. So that will be reducing your merger graph. The possibilities of combining will get reduced because multiple control signals are present in the same field.